Hello, and welcome to the Spring 2022 Clemson ECE Presentation for the Versatile Terrain Navigation of a Hexapod with a Novel Control Policy. In modern robotics, code and hardware interaction has been abstracted through the popular use of languages like Python. However, in scenarios where low latency command processing and execution are necessary, software based on these interpreted language can hinder the performance. Our team's solution was to create a modifiable robotic platform with C and C++ low-level headers to interact with the hardware much more directly. Thus, we are able to process commands in a fraction of the time and support modularity through things like I2C communication by adding peripherals to adapt to any situation at hand. And now I'd like you to say hello to our project. Say hi to the Hexapod. He says hi back. We hope this project can be expanded outside of the classroom for potential disaster relief and police and military applications. We also hope we could expand it into the consumer robot design market with advanced software headers designed for ease of use and minimalistic appearance. Here's a block diagram containing all of our subsystems. We have subsystems consisting of vision, compression of video and transfer to a host computer, I2C communication with peripherals and hardware, a primitive compiler that uses a scripting language to write to servos, a GUI that allows the user to easily interact with and gain information from the robot. And we have the sensor drivers, a module board that allows users to add and remove different modules depending on the situation. Given that this project was software oriented, we used the C language to interact with the hardware that was included in the project. We used the PCA 9685 and the ADS 7830 to interface with our servo motors and our peripherals attached to the robot. Here's a clip of the robot showing you some of the things it can do. It has an LCD screen attached to the peripheral board and motors mounted to the head to allow it to look and nod and give you a response.
Hey Hexapod, would you like to tell the viewers about yourself?
As I said before, this project was primarily concerning the software side of things. However, that doesn't mean we didn't have to interface with some hardware. On the left, in the top, are the PCA 9685 chips that allowed us to interface with the legs on the servos, allowing for advanced movement, which we'll get to a little bit later. On the bottom, we had the mounting board for the peripherals that used an I2C compatible ADC to allow us to gain data from the sensors and pass it to the limited GPIO pins. We used many variations of the wiring Pi library to receive the sensor inputs and interact with the hardware. Here are some of the sensors we selected to integrate into our Hexapod. On the left, mounted to the forehead, you can see an infrared light-based sensor that allows us to distinguish depths of 4 to 50 centimeters. And on the right, you can see a pressure sensor that was originally mounted to the feet of the robot. However, due to their small size and difficulty to validate sensitivity ranges, these were not included in the final design. Now, we can finally talk about that software that I've been mentioning. As the process initiates, a primitive compiler puts together all of the primitives or frames, similar to frames in an animation, that allow the robot to move. The depth and pressure sensors continually gather information, and the command line interface of the GUI collects user input. This input can be interpreted as text commands displayed on the LCD screen, imperatives to give you data on the robot, and movement commands, which will execute those primitive movements.
So a pretty central part of our design philosophy was eliminating redundancy in the existing code. To that end, we kind of started this project inheriting nothing from the existing software. We thought about things that existed in a very conceptual way. We thought about how we might do those things better, what we what we might want to keep from that project, and how we might do things better ourselves. And what we ended up going with was an entirely novel solution, implementing something called a movement queue. And the movement queue is, I guess, the highest level construct that exists within our code, because it is comprised of a number of different primitives, the primitives themselves comprised of different frames, as alluded to in previous slides. Now, this is really significant because this basically takes very primitive movement patterns and it makes them discrete, which is useful when you're running this bot, not only because it makes memory very sparse, but also because it makes memory very reliable. By queuing up these basic movements, we can not only ensure that for a broken pipe, that is, broken networking between the user and the bot, we can stop movement very, very quickly at the termination of a primitive. It also means that we can create very complex movement schemes by basically defining patterns of iteration through these existing regions of memories. This is very fast, it's very sparse in terms of stack usage, and of course, the latency is quite low as we intended. So of course, another very large part of our project was a GUI. We needed some sort of graphical interface for the user to control the bot through. That was a part of the bot and its previous software, not something that we wanted to neglect in our reproduction. We used a library called ncurses. It's very fast to update the screen. We don't have to rasterize. We can address specific characters. And furthermore, unlike the last GUI, this is actually layered over the terminal, which means that standard input buffering is done by the terminal, and it's simply reflected on the GUI when we choose to update certain fields. So here we have the GUI in action. You can see up in the top left there, that's the gimbal position. As the head moves, a small dot moves within a fixed region to show how far left, right, up, or down it is with respect to its physical confines. Up to the right of that dot, you can see voltage. That's basically an output from a distance sensor. Toward the bottom, that's basically a command line that exists within the GUI. That's something that I coded to understand a number of different inputs. You can see there, we just started a resource monitor. Here we're doing a capture, an image named testimage.png. And in the bottom left corner of the screen, you can see contact sensors and their outputs. Now here, I'm running help. It shows a number of different functions. The ADC here was read. You can do an I2C flush, which basically just resets the registers on the bot. And that's something that was not absent in our GUI, nor was it present in theirs. Again, a big part of our project was this very congruous union between software and hardware. And here with this GUI, you can be very careful with how much is being used.
In order to reduce the load on the Raspberry Pi, a constant video stream was set up using VLC, the Raspberry Pi camera, and a RaspBiCam function with a 264 codec and HTTP protocol to a host computer. The host computer will then take the video and, using a combination of OpenCV, which is a computer vision library developed by Intel with C++ functionality, and YOLO v3, which is a pre-trained deep neural network trained for object detection, will analyze each video frame and identify possible obstacles. Most of the limitations from this process resulted from the lack of processing power from the Raspberry Pi and the fact that the host computer, which is running a deep neural network, did not have a GPU but only a CPU, resulting in some overhead.
Here's a short demonstration of our object detection and use. This video was taken in the lab as we were working on the project. And now we will analyze the performance of the bot. First, we will look at the hardware specs. As you can see from this chart, the voltage is consistent across all different kinds of performance. Current draw ranges from 0.005 amps all the way up to 8 amps for a heavy load. This large current draw made it difficult to find an appropriate power source to power the bot consistently. As you can see, it required a lot of power in light load and heavy load operation, which it is often in between. One of the main metrics we wanted to gauge our success on was the efficacy of our code. As you can see here, our command latency is about 5 milliseconds, compared to the 153 milliseconds of its Python counterpart. Our vision latency, highly dependent on data type and network conditions, ranged from about 3 to 7 seconds. Our memory usage on average for the primitives was about 2.63 kilobytes, and our CPU usage on the Raspberry Pi was about 34%. As a part of this project, we also wanted to quantify some of the locomotion and physical stature results. In our problem statement, we wanted to be able to move through difficult terrain, including tunnels, over objects, and other various obstacles. The height profile ranges from 6.25 inches to 11.25 inches, depending on the mode. The normal walk on a flat surface was able to go about 5 inches per stride, or movement cycle. The tall walk, as seen in the locomotion video, went about 3.25 inches. The squatted walk, the low-hanging walk, went about 4, and the side steps each went about 1.5. The bot also rotates about 15 degrees each time the command is input. The vision latency before grayscale was about 5 to 7 seconds. The H.264 codec had a 60:1 compression ratio and a desired compression rate of about 141.96 kilobits per second. For a hypothetical test of a 500 kilobyte video, the non-compressed would take about 26 seconds and the compressed about 0.41 seconds plus the overhead. As for YOLO, it was 95% accurate for programmed objects and had various success with non-programmed objects. One of the greatest strengths of this project is that it is exceptionally fast. By implementing compiled C code rather than interpreted Python code, we were able to beat the previous implementation by over 100 milliseconds. This project is secure and usable. The GUI is easy to use, informative about the resource usage and performance of the system, and provides security for both the software memory and hardware performance. We also like to brag that this was a pretty creative solution. As stated in the title, this was novel and built from scratch, and thus we put a lot of heart and work into this. Also, we'd like to highlight that it is modularly designed. Thus, it is a platform that can be expanded by consumers, police officers, military, search and rescue specialists, and many others. One of the biggest bottlenecks to this project's progress was an inconsistent network connection. Due to edge-a-roam limiting the connection from outside devices, we were forced to implement a Wi-Fi hotspot. This Wi-Fi hotspot was tethered to the Hexapod, however, it used the same UART bus to connect to the Pi. Many other devices on the Pi connected through this bus, and thus the connection was not always consistent. Shaking or moving would often break the connection, restricting the vision, the commands, and the overall performance of the bot. The leg traction and movement had varying degrees of success dependent on the material it was placed on. The legs lacked a lot of traction and had a difficult time going up inclines and would often get caught on certain objects in the way. Also, given the background of most of this team as computer engineers, certain aspects were neglected due to our focus on the software side of things. Our team would like to thank Dr. Raza for his help throughout this semester. His flexibility, patience, and guidance have helped us progress through this project and build something that we can really be proud of. We would also like to thank the Department of Electrical and Computer Engineering for both funding and accommodations through the use of the Senior Design Lab and partial funding for the project. And here's some of our references.